In terms of algebra, when we do such derivation, there are a lot of steps, and most of the time you need to be like very careful while going through like the rigorous maths. Um, and the intuition most of the time comes at the very end. So it's like it takes a lot of patience to just go through the entire derivation and then make sense out of it at the very end. So like this lecture might get a little boring because I will also struggle deriving it because like all the steps are not as easy. Um, but one thing's for sure, like once we get through it, um, the intuition and the physics that comes out of the final equation is really nice, and that we can understand later uh, by a lot of examples. So, but it's still important to at least once go through this derivation, derive it for yourself, um, and be confident with all the steps because it's like most of the time you won't be asked to like derive this or derive most of the things if you are like an experimental researcher, but generally theory groups do this. But it's important, I guess, even for experimental people to understand the derivations first because the derivations sort of have a flow. And first thing is like formulating the problem, and then you go through the algebra, then you get a final equation, then you solve that equation, and then the solutions of that equation is actually what you do physics with. Like you experimentally verify those and see the populations and everything. But yeah, so like the point being, even though you're not required to do it most of the time in the real world, um, as an experimental person, still sometimes it is good to go back to derivations and like do the math rigorously because some of the steps here gives you like a lot of intuition on how to think about a problem, and even like some algebra that we are going to do here is like when we are doing quantum physics, um, it is like these steps are really like important in terms of there are projections that we are going to do on specific states. We are going to solve Schrodinger's time-dependent equation, um, and we are then going to analyze the solutions. First, we will get a coupled set of differential equations. So yeah, it is like all of these steps involve some intuition behind it, and it is like nice to follow a recipe um, whenever we are going through a derivation. So it is, it's not uh, like going through derivations is like kind of boring. Even I find it a little boring whenever I'm doing math, and that is like that is even my weak point. That's why I chose not to be a not to pursue theoretical physics. So you can even see you will even see in this lecture that I will miss some steps. Maybe I will make some blunders. Um, so I guess that is the point when you can point it out, and then we can work it out together in this derivation. And once we are through with that derivation, then I think then we can discuss like the beautiful physics behind it. So some of it, some most of it, it's just math, but I think it's still important to go through it at least once, even by yourself. Even after the lecture, you should derive it by yourself and see how each steps comes. I might not even do all the steps. So because yeah, I'm being selfish that I have gone through it by myself, but I think you guys should go through it by yourself as well. So yeah, um, I guess 8 people are here. Yeah, can wait maybe a few minutes more. And also, I think there are two or three ways, I guess, to go about this derivation. Um, some prefer Schrodinger's picture. In Schrodinger's pic there are three pictures that we can do quantum physics with. One is Schrodinger's picture where state vectors carry the time dependencies. There is a Heisenberg picture where the operators carry the time dependencies, and there is interaction picture where um, you can do it using both uh, carrying time dependencies. So, interaction picture actually helps you a lot when you are doing physics with just like transitions. When you are doing when you are basically interested in the interaction and not like the state depend like the not the exactly solvable part because you already know the solutions of the system, then interaction picture is very useful. But there is a way to go from Schrodinger's picture to interaction picture, or like there is a way to transform basically between different pictures of quantum physics, and I think that also you can see in many textbooks. There is like a proper way to do it. But yeah, you can do uh, quantum physics with all three different pictures. It's just that some of the algebra changes, but it is just a transformation. It's like going from one frame to another frame. So the physics doesn't change much, but the way you derive things and the way you interpret things, that changes depending on which picture you are in. So, I think we'll follow Schrodinger's picture in this derivation mostly, but I can give you one or two uh, snippets, I guess, to go to interaction picture. How how will that look like? I will also send maybe after the lecture, um, sometime midweek, I will also send maybe the explicit derivation the way I'm used to doing it, because we may skip some steps in the build up in the lecture, but you should do it yourself again. But I will send the explicit derivation with all the steps included, because I don't think even in for seafood book it doesn't give all the steps, but most of the algebra I think you can go through it if you do it carefully on the paper. So maybe Nitin sir is not joining you today as well, I guess. Okay, so I will maybe start with the derivation. Um, so I think we are going to start with just Schrodinger's time-dependent equation. The problem that we want to solve is if we have so if we have an atom which is like a two-level system that is interacting with light, then so maybe first we can write down our problem statement. So problem statement. So what's the problem that we want to solve? Um, is we have an atom which is like a two-level system that is interacting with the light, which we can imagine as a changing electric field, oscillating electric field. So which is monochromatic, so has a single frequency. If we imagine that, then basically imagining light as an electromagnetic wave. So this actually is a imagining atom as a two-level system is actually a quantum mechanical thing. So this is QM treatment, and imagining light as an electromagnetic wave is classical. We can do it the other way around as well. We can treat both of them classical and still do still solve it. We can we can put both of them as classical. So this will be a classical way of doing it. Then we can put both of them as quantum mechanical, where now the okay, so light is classical here, classical treatment. So if we treat both of them quantum mechanically, what by that what I mean is if you want to treat atom uh, classically, then you can think of atom as being like a dipole, just a dipole where you have an electron, which is the electron cloud around the nucleus. So you can treat it like that, or you can treat it like a two-level system. Um, Still, like the formalisms kind of merge when you do like the results kind of merge, the formalisms are different. So you can treat the atom as classical or as a quantum mechanical thing. You can treat the electromagnetic wave light as again quantum mechanical thing or classical thing. If you want to treat light as a quantum mechanical thing, then you have to treat it as a stream of photons. So there are two ways to do it again with light. So it's like you can treat both of them classically and have a classical treatment. You can treat both of them quantum mechanically and have a QM treatment, or you can treat like we are going to do here. You can treat one of them as quantum mechanical thing and another as classical. So this approach is semi-classical approach. If you want to do both of them quantum mechanically, then you can follow the spec book, which I think I sent the PDF of. And this treatment, semi-classical treatment, is done, I think, in foot. So we don't do both of them classically because the like that is like somewhat now we have to incorporate quantum physics in that because it gives us beautiful results and that matches with our experiment as well. So there are two ways to do this derivation. There's not much difference. There is not much difference, but treating light as a quantum mechanical object requires, again, I think, some additional quantization, which is like a second quantization. But we will maybe cover it later, but I don't think we'll do it from the start because that will get a little more complicated. So what we are going to do is we are going to treat the atom as a two-level system. That's why that's a quantum mechanical thing treatment, and light as a classical uh, light with a classical treatment, which is imagining light as the electromagnetic wave. So that's why this is the treatment that we are going to follow, and which is a semi-classical treatment. So this is like the problem statement that if we have an atom and if we have light incident on it, which is generally laser light in the lab, then we can imagine the light as a changing electric field, and that electric field, if we have implemented on an atom, how will that behave, or how will the energy levels change, and what will be the time evolution? What are the probabilities of finding the population in one of those two levels? So basically, the problem narrows down to we have two levels where we have a ground state and we have an excited state of an atom, and we have imparted a laser on it. So if we impart a laser on it with some, uh, you can then imagine this as a stream of photons or changing electric field. So then, if you imagine this as a changing electric field, what you are imagining is It's time-varying electric field, so it has an amplitude and an oscillation frequency. So if this is your field, then what you are doing, okay, so this is vector. And if you now, yeah, so this is light and this is the atom. So atom is a two-level system. So then you have one electron, and that electron starts at the ground state. Um, Whenever, because it's a stable state, and whenever you incident a frequency of omega naught, let's say, then this is the resonant frequency where from using which you can go from the ground state to the excited state. So um, if we do this transition, then we already talked about the things that can happen. What are the processes that are involved when you are doing transitions with light? One of them is stimulated emission, stimulated absorption. So by stimulated absorption and emission, what do we mean is if we incident the laser on an atom, or looking at the specific two levels at a specific frequency, then we will carry out the transitions between those levels. So if laser is responsible for carrying out these transitions, then those are called as stimulated absorption and emission. So the laser takes it up and the laser again takes it down. Or there is another way by which it can come down is the spontaneous decay. So the spontaneous emission also can occur. So to take into account the spontaneous emission, if we want to understand that as well, which we are not going to do with, uh, in the first thing, because in the first thing we are just going to assume that the system is closed, in the sense that it's not interacting with the environment. So there are uh, there are different ways of doing quantum physics, and that is why we because later we want to incorporate even the environment. That's why we introduced density matrices. But so that approach, when we will consider the spontaneous emission, that approach I think is the open system approach. So open is basically when you have a and environment, system and environment, and then this is the total thing that you are going to see. And then if there is an exchange between system and environment, then it is called as an open system. Otherwise, it's a closed system. So to understand spontaneous emissions, we have to understand in terms of open systems, because it is because of the interaction with vacuum, the spontaneous emission happen. If you don't consider interactions with vacuum, then your electron will not spontaneously come down. So we are first going to solve everything just to understand in terms of stimulated emission, stimulated absorption and emission processes. So for these actually only the laser is responsible. So this is like the background of this is like our problem statement that if the laser is interacting with the atom, then we are going to consider atom as a two-level system. We are going to consider laser as a classical wave, and then we are going to solve it and understand. First, we'll just talk about Hermitian quantum physics, where you're basically considering just the stimulated part, and then if you want to include open system approach and if you want to consider spontaneous emission as well, then you will have to take into account both the interaction between the system itself with the light and system with the environment as well. So we'll do that maybe later, but we'll start with just the simple interaction of two-level system with a classical wave. So that is the problem statement that we have. So to start with, we'll start with Schrodinger's time-dependent equation. Uh, so this is Schrodinger's time-dependent equation in equation one. Um, so I h bar d psi by dt is Hamiltonian is same as if you can equate it with Hamiltonian operating on the wave function, where psi is the total wave function of our system. So it is position and time dependent. So this is a function of space and it is a function of time, both. But this is actually a wave function that is an eigenstate of the total Hamiltonian. And the total Hamiltonian H has two parts, where H0 is the uh, initial Hamiltonian of just the atom, which is we call it as a bare atom. Uh, there is a terminology in atomic physics where you consider if there are two systems and you also want to consider the interaction between those, then first you consider the bare states. What do you mean by bare states? Is if the interaction was zero, if there was no interaction between light and atom, then what would be the Hamiltonian? So if that Hamiltonian, if we take and then we solve the system, then we'll get the energy eigenstates of just the atom. So here we will have just two states because we have two level system. But if we have a real atom, then the system's energy eigenstates will be just the sum of all those. So the superposition of all the states that are possible. So in hydrogen atom, if we take if you want to solve a real problem and if you want to take hydrogen atom, that as well we can do by just summing over all the states. But why we can do it by just considering two levels is because we have tuned the laser to such a fine extent that we can neglect the connection or the interaction with the other levels. So that's why if we are focusing on a specific transition and other levels are far off, then they are still probable, but then we can neglect the interaction with those levels. That's why we can consider two level system. So what is the total Hamiltonian for our system is the initial Hamiltonian of the atom, for which you can understand that for both these levels are energy eigenstates of the bare Hamiltonian, H naught. So that's why if you operate it on the state, you will get back the energy eigenvalue for that state. And if you operate it on the second state, so first state is the ground state, and the second state is the excited state. So you'll get energy one and energy two. And like we were talking about here, uh, this is this is E2, this is E1. Sorry, E2, this is E1. And the energy difference between these two is h bar omega. So this is the transition between the two. Now, so we have energy eigenstates. So one and two basically are energy eigenstates of the bare Hamiltonian. Uh, so now if we want to write in terms of the total Hamiltonian, then psi, uh, which has the space and the time part, is the energy eigenstates of the total Hamiltonian. So now total Hamiltonian, in addition to the atom's bare Hamiltonian, what does it have? It has the interaction Hamiltonian as well. And the interaction Hamiltonian has a form where you consider that the atom is acting as a dipole. So if you consider that the atom is acting as a dipole, so basically you are considering a charge. So what that charge is basically the charge difference between these two levels. So you can consider a nucleus and then let's say an electron, and then there is a charge Q. This is plus Q, this is minus Q, and then there is a distance r between them. So then QR is the dipole moment. So here in our case, this is transition dipole moment. Why is it transition dipole moment? Is because if you will get only dipole moment whenever you're considering the transition between the first state and the second state. You won't get any dipole moment if you're considering just from one to one, because there is no transition happening, there is no energy difference between these two, there is no separation between these two. So if you get one to one or two to two, that won't give you any dipole moment. So the dipole moment will only exist between going from one to two or two to one. So that's why we have this dipole moment, and it is kind of like you can imagine states one and two are coupling because of the light coming in. because there is a charge difference between these two, and that is how we consider the atom as an oscillating dipole, that you're going from one configuration which is in the first orbit to another configuration which is in the second orbit. And then you can already imagine that s orbit is like a sphere and the p orbit is like a uh, dumbbell shaped. So when you're going from this transformation to that transformation, you're actually oscillating the dipole in different ways, and that oscillation gives you the dipole moment. So you can't have dipole moment if you're just going from one to one, if you're staying in one or if you're staying in two. So there has to be a change in your dipole moment. So then there has to be a change in your charge configuration, and that will give you the dipole moment. So that's why the interaction Hamiltonian will, if you know from electrodynamics, the so this is directly from electrodynamics, that energy of a dipole in oscillating electric field is just given as energy is equal to minus d e, where both of these are vectors. And the scalar product between them is a scalar. So energy is a scalar. So this can also be written as E R bar. And so how I understand it, how I quickly check if this makes sense to me in terms of just dimensions, is always I remember that the force due to any electric field on a charge is just QE, and then the energy, since always that we have imagined energy in terms of force and the displacement. So then this R becomes the displacement. So then that's why energy of an oscillating dipole is like this. And this makes sense to us. So for us, the E bar is actually E naught cos omega t. So this will be our interaction Hamiltonian's form. And this is actually the energy of the dipole, energy of an oscillating dipole in an external electric field, in a changing external electric field. So this is the additional interaction Hamiltonian part, which we are going to add to our bare Hamiltonian. And our bare Hamiltonian was just two-level system Hamiltonian, where you have the first state, um, and you have, so the first state is ground state, and then you have the excited state. Um, and this note, I hope this notation is familiar to you. This is an outer product. So if you want to write in terms of projection operators, you write it in terms of outer products, because this is um, because this here is an outer product and it's not an inner product, so it's not a scalar. Um, but it is a matrix, and Hamiltonians are operators, so they have to be a matrix. So this is how we can write Hamiltonian for the two-level system. So this is a two-level system Hamiltonian, which is the bare Hamiltonian, and we can directly see why these are they have eigenstates is because if you project it on the first state and the second state, second energy eigenstate, you will get one and two with these energy levels, which is E1 and E2. So it's very easy to formulate these things. So that's why we have this H naught and Hi, and the total H is given as H is equal to H naught plus Hi. So this is the interaction Hamiltonian plus H naught, and the eigenstate of this is psi. So we can write in terms of, again, Schrodinger's time dependent equation, where we can say that this is true, where psi is defined as the total wave function. So the form for psi now becomes, in terms of the energy eigenstates, the energy eigenstates are 1 and 2, but there is another e to the minus I omega t, because again, so I think we already know this, but still, if we want to write the total wave function in terms of the energy eigenstates, how we do it is we e to the power I e t by h bar. and I this is actually whenever you're doing this gives you the Hamiltonian, and from if you operate it then on a psi, then that will give you in time evolution you will get here and E naught. So if you want to go from a stationary state psi naught to a total wave function psi r of r and t, then you can do this transformation after solving the Schrodinger. So we were talking about the recipe in quantum physics. So that recipe is, of course, first get Schrodinger's time independent equation solution that will give you psi naught. Psi naught is energy eigenstates for any system. So that we already know for our two-level system because there are just two levels and those two levels are energy eigenstates. So we already know psi naught and that is the energy eigenstate of H naught. So once we know psi naught, we just have to time evolve them. So with some coefficients, so that's why you will get that's why this is of this form and which with each energy level E1 and E2. So then if you write it in that form for both the energy levels, if you want to consider both the energy levels, then your total wave function for the final Hamiltonian's eigenstate becomes psi of psi depends on both again space and time coordinates. The first coefficient now gets a time dependence because the time dependence will also be in the coefficient as well as in the phase. Because earlier we didn't have this because now actually both the levels can interact with each other because of the interaction that we are keeping. So the coefficients will change. So if the electron is in the ground state at the start, then because of the interaction, the electron can now be in the excited state as well, or can come again back in the ground state. So that's why when we see the interaction happening, and if we see after a certain amount of time, the coefficients are now time dependent because they can change because we have kept an interaction between the two levels. So the coefficients were steady. So the C1 was 1 and C2 was 0. C1 is the coefficient where C1 square gives you the probability of electron being in the ground state, and C2 is the coefficient for the excited state, where C2 square gives you the probability of being in the excited state. But probability of being in the ground state or the excited state are changing with respect to time. They are a function of it is a function of time because we have kept uh, a light coming in that connects these two levels. So that's why the time dependencies are also in the coefficients. So if you want to write down the total wave function, then you can construct that wave function. So this is the construction. We have not solved it yet, but we can construct this wave function of the total Hamiltonian um, to be like this, where C1 is the coefficient of being in the first level. That is time dependent. So that's why there is a time dependence shown here. Then the first excited, sorry, the ground state, and you will get the phase factor, which is e to the power minus I omega t, which is omega is basically E1 by H bar. That comes from the time evolution part. So, and the same thing will be for the second state. So ground state and excited state both will contribute in the final wave function that we have constructed. So now what we want to know here is what are these coefficients C1 and C2? We have constructed them, but we don't know what's the value for these two coefficients as we go forward in time. What's the time dependence? So that's what we actually wanted to know. Because we want to know the time evolution of the system. We already know the energy levels that are present in the atom. So what is there to find out now is if we interact this two-level system with the light, how will the system evolve as a function of time? That's what we want to know. And like we discussed in earlier lectures as well, that depends on the energy dynamics of the system. And that's why we are connecting this to the Hamiltonian. And that's why we're connecting it to the interaction energies. And then we will get out uh, the time evolution of the system, which is what we want to know. That how the populations change in a system whenever we have imparted light as a changing electric field. So we have constructed this this psi total psi. So let this be equation number two. So what we are going to do is we are going to substitute the total Hamiltonian in the right hand side of the Schrodinger's time dependent equation, and then solve it, solve the right hand side, then take a time derivative of this total psi on the left hand side, and then equate the two. By equating the two, we will get a coupled equation, and then we'll solve that coupled equation to get our solutions. So, okay, so let's get down to it. Um, so the total Hamiltonian H will be sum of the two, and the total Hamiltonian looks like this. So now if we operate this on the psi, um, so first we'll let's again write the Schrodinger's time dependent equation, which is just H. So now let's solve for the left hand side. So this is I h bar d by dt of psi, where now we know that the total wave function psi which we have constructed by ourselves because we know the energy eigenstates of the system already. So we know that psi is a function of both position and time, and that can be written in terms of the first and second excited state, sorry, first and second state, which is the ground and excited state in the atom. So, which we can write as, I hope everyone is familiar with the bracket notation. So this is the ket for this is the first energy eigenstate of the system. Um, and then we'll get this. So we have just substituted psi from equation 2 in this. So since both of these carry time dependencies, both these terms are time dependent, but this term is not time dependent. So then we can take this out. So again, chain rule, simple algebra. If we do that, what we will get is, let's write in the simple form. So first we will get a time derivative for this, and the rest of the terms remain the same. Then in the second, we will use this derivative on the second term of the first. So minus I omega 1 t, and you will get minus I omega 1 as the extra part. Because if you take a time derivative, then time derivative of exponential is just that, but the coefficient's time derivative, the coefficient comes down. So that's why you get this. Similarly, in the second term, you will get again the same thing. At any step, if you want me to go slow, just tell me, but I think this is pretty trivial. That's why I'm not. So you can actually combine this term and this term together. Um, how you can do that is, so you already know that E2 minus E1 is h bar omega 2 minus omega 1, which we have written as h bar omega naught. So then if you want to write in terms of h bar omega naught, then we can write like this. So if we simplify, then we get this term and this term. They remain unchanged. So we get this plus. So this is time derivative. So I hope this notation is also clear that when I write c dot, it is basically I'm writing dc by dt or partial derivative, I guess. So not a full derivative, but so this is the notation. Um, so we'll get this minus I t, and then we want to combine these two terms. If we want to combine these two terms, we will have to multiply the first one by a negative sign. So we will do that. We'll get a negative sign outside extra. So let's say this. So if we want to combine these two terms, but if you notice these two terms have a different coefficients, so we directly can't combine. So in order to get rid of those coefficients, we will have to multiply by 1 and 2, but we'll do that. I think I'll write for the simplicity to understand later. I'll just write both of them together. Plus, you can clearly see that this is like this is a weak point of like an experimental person where I am missing signs and doing random things. But okay. So this equation, if we want to modify later, we'll modify. But for now, let this be equation 4. So now, and later we want to combine this bracket basically, these two terms, which we will do by multiplying with psi, but we'll do that maybe later. So first, now we need to solve this, which is the right hand side. So this is operated on psi total, so which is our right hand side. Because at first we were solving the left hand side of this time dependent equation. So if this is the right hand side, um, then this is again a pain to write. So we can do it in a simpler way, but just to be explicit, I'll maybe solve it individually. So if this is operated on this, what we'll get is these. So this psi naught has C1, which is time dependent, then e to the power minus I omega 1 t. But notice that none of these, it's not if operated on all of these, then you get nothing. So that's why it comes out as a constant. It's not dependent on that. So what it is dependent on, or what can it be operated on, is the first energy eigenstate. So the first energy eigenstate, did we get any messages? Oh, it's maybe my phone, but that's fine. Okay, so yeah, we were here and we are substituting psi naught. We are substituting psi in terms of the two energy eigenstates. So we'll get e to the minus I omega 2t. And the second 1 and 2 here are the energy eigenstates. So we already know from at the start, we said that the ground state is energy eigenstate of the bare Hamiltonian and also the excited state. So we'll get E1 and E2 back. So if H naught is operated on the total wave function psi, what we get is simply C1 of t, then E1 and 1 e to the minus I omega 1 t plus C2 of t E2 e to the minus I omega 2 t. So we get this simple expression, which let that be equation 5. And then we can operate H interaction on psi. So again, H interaction for us is minus ER E0 cos omega t. So now, and this is the dipole moment, and this is the electric field. So this is basically the same thing. And this is operated on psi. So now we actually want to write this in terms of um, like a simpler notation. If we want to do that, then we can go to like a different because this interaction picture, this actually simplifies a lot, because in interaction picture we can directly write this Schrodinger's time dependent equation as when we consider psi as the energy eigenstates of the interaction Hamiltonian. So in the interaction picture, actually we'll get directly the expression in terms of where now psi is not psi is the eigenstate of the interaction Hamiltonian and not the original total Hamiltonian. So in this picture, actually it simplifies a lot, but just to explain you a normal uh, state dependent Schrodinger's picture, we will solve just for Schrodinger's picture. So if we apply now this operator on psi, then first thing we can write E as so. Okay, so later we will. Okay, so what's our aim? The aim here is to write this operator form in the final form, which is h bar omega by 2 e to the I omega t plus e to the minus I omega t omega 1 omega 2, I guess. So we want to write in this form where omega is the Rabi frequency, where we have ER, E naught by h bar. So this is the transition matrix element. So if you're going from one state, which is the ground state, to the second state, which is the excited state, through the laser, because of the laser, then this comes out and the time dependencies are still. So actually, what we have done here is just multiplied from the left by uh, one of the energy eigenstates. So since we want to write it in this form, what we will do is we will multiply first by the first state, and then we'll multiply it. So basically what we want to do is we have this expression, which is, let's say, expression 6. So expression 4 is the left hand side of, so we are only focusing on one equation, which is Schrodinger's time dependent equation, and that time dependent equation is this. So the left hand side of the time dependent equation is just IH bar time derivative, which is the equation 4. So equation 4 is the left hand side, and equation 5 plus 6 gives you the right hand side of the Schrodinger's time dependent equation. So what we are going to do is we are going to project the left hand side and right hand side on the energy eigenstates 1 and 2. So we are going to, what do we mean by we are going to project is we are going to pre-multiply and post-multiply. Um, we are going to pre-multiply by 1 on both sides. So if we do that, then what this equation looks like then is, so psi 1, you can write psi 1 or, so okay, first let's not get confused in the notation. So when I write 1, it is same as psi 1, which is the energy eigenstate of the bare Hamiltonian H naught, which is basically the ground state. And similarly, if I'm writing 2, then this is excited state, ground state. This is 2. So what I'm going to do is pre-multiply by 1 to the entire left-hand side. What that gives me is uh, before we do that multiplication. So you know that these two states are orthonormal. So if I'm pre-multiplying and if I have a ket vector like this, then this bracket will give me 1. Then if I have it like this, it will give me 0. And if I have it like this, it will again give me 1. Because these two are normal, because these two are energy eigenstates of the bare Hamiltonian, they are orthonormal. So what do you mean by orthonormal is they are orthogonal and also normalized. So if they are normalized, then if you have a bracket which is like a normalization, then you get 1. And similarly for the excited state, you get 1 if you multiply bra and the ket. Uh, that is basically you are normalizing, you are projecting on the same state, that's why you get 1. And if you are projecting on some state which is perpendicular to it, then it doesn't have any contribution in that direction. It's like projecting I cap on j cap, you'll get 0. But if you project I cap on I cap, you'll get 1. So that is what we are doing here. That if we, because in order to proceed, we need to confirm this. So make sure that you understand this, why this is true, because this will be used when we are projecting on the first and the second state. So then how our equation, so initially our equation looks like this, IH bar del psi by del t. Now what we want to do a transformation is we want to do this IH bar del psi by del. So now 1, if we do that, then how does our expression change? So we had equation 4. So equation 4 looks like this. So if we multiply now, if we pre-multiply now by 1, if we project it on the first state, which is the ground state, you can see that this factor is going to be 1 because it is an energy eigenstate, it is not time dependent, so it is not going to interact with, or it is not going to get multiplied with the time dependent part. So this is a constant for it, this is a constant for it, it is only going to interact with the ket. So and if it interacts with that, you will get just 1. If it interacts with this, uh, what do I mean by interact is basically uh, it will get projected on that, and then you will get some simplification. So if you directly have a multiplication of 1 and 2, you'll get 0. But if you have some part in between, then you will not get 0. So then again, the same expression 4, we are going to write in terms of this. So this is going to get 0, and we are going to get a time dependent part here, and this will be 1. So this actually has a time dependent time dependence in between. So um, what we want to do is we want to write this, and we also want to write later. These two are basically transformations which we are doing on both sides. So this is left hand side, and we are going to do the same thing on the right hand side, and equate those two expressions so that we get a coupled differential equation. So if we simplify like that, then uh, since I don't want to go through each step, I'll just refer to this book. So if we go through whatever we have done till now in the lecture, we have just we have just covered like 2 pages of this chapter. But it takes some time to go through this chapter because there are some prerequisites that we want to know, and that's why setting up these equations, I think, was like today's aim for me to get to like the coupled equations. So at the start, it also says the same thing that we discussed in this chapter. that the radiation is treated here as a classical electric field, and we are going to treat the atom as a quantum mechanical thing. So we are going to solve this time-dependent Schrodinger's equation, and so the book also starts with time-dependent Schrodinger's equation, where the Hamiltonian has two parts, the bare Hamiltonian and the interaction Hamiltonian. Then it says that the total wave function can be written as the in terms of the energy eigenstates, so which we have talked about here. Why I'm going through the book is because whenever we are doing uh, like using a different notation or using a different formalism, it is good to go back to the book and see their formalism and see if our thing matches with that. So let's make sure that we are not missing any part. So if we have it, so yeah, we talked about this, that we had equation for exactly like this, that this is the total wave function, um, which we have taken time derivative of, and then that gives us the left hand side of the Schrodinger's equation. And the interaction Hamiltonian is again d dot E. You can see that this is d and this is E. So d dot E. And once you substitute that, you are going to get this final uh, equation, which is coupled equation basically. So you are going to get a coupled equation where omega is the Rabi frequency. So I think this would be, because we are completing an hour, this would be a great exercise. That so what I'm going to do is, because this will take a lot of time if I write it out, but what you need to do is write the left hand side of the equation, project it on the first eigenstate, write the right hand side of the equation, project it on the first eigenstate, then do the same thing with the second eigenstate, and then combine these two. If you combine these two, then you'll get a coupled differential equation, which is in terms of the C1 and C2 coefficients. So uh, we, I think for us to move forward, you need to sort of derive these two things. Why I'm not deriving them explicitly right now is because this will take a lot of time if I write it down, write all the algebra. So what I'm going to do instead is maybe type it out and send it to you, and then we can go through that each step maybe again. So for the time being, where we are right now is just till 7.8 in this chapter, and then to go from 7.8 to 7.9 and 10, which are like the coupled time dependent equations, differential equations, you need to do um, you need to solve Schrodinger's time dependent equation. uh, Not even solve, you need to just substitute the wave function, total wave function, and the total Hamiltonian on the left and right hand side, and then equate the two and get these two equations from those. So equation 7.9 and 7.10, how to get that from starting from 7.6 and 7.1. I think that will be like a good task for you to do in between these lectures. So in the next lecture, I think where we will start is we'll start from these two equations. What I'm going to do is maybe give you the explicit steps by writing it out in on a piece of paper, and then send it to you guys. We will maybe go through them quickly when we are starting the next lecture. But we will start from these equations, uh, and then we will go on solving those equations, where we'll put the initial conditions. So I think because I want to break this lecture down into three different lectures, where we are in the two lectures we are deriving things, and in the third lecture we are explaining the solutions. So I think for today, I just wanted to stop here. The reason being, I have not written down yet the complete steps to go from 7.8 to 7.9 and 10. But if I write it out, it is a lot of algebra, and I'm sure I'm going to make mistakes. So instead, what you can do is you can also try it out. You can try to go from 7.8 to 7.9. Uh, and I will also do it, and I will send you like the proper notes how to go from first equation to the second equation. But if you think about it, it doesn't involve a lot of steps. But make sure you go through with it. You try it first, and then whenever I prepare that document, I will send it to you, and then we can go through it together in the second lecture, in the next lecture. Because in the next lecture, what we are going to do is hopefully we will cover this out, and then uh, find the motivation, like what's the motivation behind rotating wave approximation. And then once we do that, we get coefficients, and then we connect it to Einstein's A and B coefficients, which gives us the stimulated emission and spontaneous emission part. So I think this is a good point in the derivation to stop here. But in today's lecture, actually, we just covered what is the formalism that we were required, and why. Now I think you can see why I stressed so much on the dipole approximation, why I stress so much on the two-level system, and why I was talking about light as a harmonic oscillator. Actually, the third part, the light as a harmonic oscillator, is only going to come when we are considering the quantum mechanical treatment, even with light. So right now, because we are doing a semi-classical treatment, that won't come in so soon, but that's why we started with those. And as you can see, if you read this chapter 7, which also again another thing I recommend, that if you go through chapter 7, then these lectures will be nice thing to be learn in parallel for you guys. And then if you read through chapter 7, then you will understand why even we were talking about density matrices in the first place. Because I think this book uh, in the later part uses density matrix approach, which is on page 129. So here they talk about density matrices, and then density matrices is also another framework in which we are going to solve these equations. And why density matrix approach then will give you a simpler way of doing the same exact derivation. We will see that but first we will do the same derivation with state dependent vectors, which is like the Schrodinger's picture, and then later we'll go on doing density matrix, because density matrix will help us uh, do it in open quantum systems. So I think this is like a good point to stop in this lecture. So make sure that you guys try to go from where we have stopped to equation 7.9 and 10 given in the book. There are resources online, but I encourage you to not look at those. There are solutions online, but I encourage you to not look at those. See it for yourself, try to derive it for yourself. I'll write it out in the document, and then we'll go through the exact explicit steps. Because, like I said, writing it out in the equation form, doing it as a derivation in the class will be little hectic even for you guys. It will be little boring even for us both. So that's why I'm not going to do that. But make sure you go through the math, and I'm I'm sure like this is another way of doing derivations in the class, is when you do the key steps, and then also as a student you'll also have to do it by yourself. Only when you do it by yourself, you will understand what where you are getting stuck, and the points where you are getting stuck actually needs intuition. So that's why I encourage you to uh, consider going through this. And then if not, uh, I'll make sure that whatever notes I send you, those have like the exact steps what I'm following. So you'll get to know by the end of next lecture how to go exactly in this derivation. It's just that I couldn't find the time to write down all the steps explicitly in this week. That's why I'm not going through with this. But in the next lecture, I think we will start from where we have stopped today. So this is like a good stopping point. But make sure you read chapter 7. You try this one step by yourself. The point where we will start is the coupled differential equations, where the two coefficients are coupled. So from those two equations we will start. So try to get there by on your own, and maybe I will see you in the next lecture. Yeah, in the on next Saturday, we will talk about the same. But I think theory wise, if you want to be good at derivations, I think the best way is to first try it out on yourself and then verify your solutions. So I will send you the derivation, but I encourage you to do it by yourself first. So let's stop here and then meet again next week. So unless you have any doubts, you can ask me, or we can consider that the lecture is concluded now. Did we have Nitin sir at all today? No, I guess not. Okay, that's fine. We'll see. I'll see you next Saturday, and I will maybe give you a printed, like a PDF before starting next lecture, giving explicit steps of going through this derivation, so that it will be easier for you to follow, better than my handwritten notes. So I guess I will see you guys next time. Thank you. Thank you.